I'd like to thank the organizers for putting on such a great event. As was said, I will be talking a little bit about cardiac modeling. The title of my talk is Computing the Heart, and I'll talk a little bit about what cardiac modeling is, how we do it, and what we'd like to use it for. I think that it would kind of be useful to talk about what a computer model is in general. And really at its basic, it's a simplified representation of some sort of physical system. And we simplify the representation so that we can solve the underlying physics using modern mathematics. And a lot of times, even the most simplified representation is still beyond sort of analytical, what you could do on pen and paper. So we use computational methods to augment our ability to do rapid calculations. So for example, if we're designing a microchip, and we want to understand how heat flows, we can build a simplified geometry of it, apply the laws of physics, and understand how heat will flow through the device. If we want to understand stresses on an airplane, we can build a model of it and run it through turbulence models, run it through flow simulations, and understand where stresses occur in the system. And if we want to even crash test a car virtually, now we can build a model. We know enough about the physics, we know enough about the systems that we can do full crash testing of virtual machines. Now, these type of models have immense utility. They underlie almost all of technology and engineering. No sort of modern product doesn't have some sort of element of computer modeling. They're inherently safe, and you don't have to take any risks by doing a computer model other than possibly not doing something that works because you think that it won't work. They're cost effective. You can eliminate lots of rounds of prototyping. You don't have to do nearly as much in vivo testing, in vitro testing. I heard that BMW, for example, no longer crash tests any prototype vehicles. They do all their crash testing virtually, and the first car that they crash test is one that's built off the assembly line. So that saves millions of dollars, tons of time, a lot of resources. They're also repeatable. You can eliminate a lot of the experimental variability. You can pass them from person to person. So these become a very good tool for doing basic engineering work. And really, the question is, can we benefit from kind of these observed, can we reap the benefits from applying models to biological systems? And the question is, can we take something as complex as life, as biology, and simplify it enough that we can generate some sort of computer system to understand the physics on, but not simplify it so much that we lose what's actually happening in the system? So this has been a big question for years. I think that we could look at the historical perspective of it. This was the first philosopher of science, and this is what he had to say about the use of mathematics in biology. Every attempt to employ mathematical methods in the study of biological questions must be considered profoundly irrational and contrary to the spirit of biology. If mathematical analysis should ever hold a prominent place in biology, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So this is the backdrop of kind of the history of science, of the use of mathematics, that they were very, very separate fields. And it's taken us hundreds of years to understand really why this is. And really the biggest reason is that biological systems are highly complex. If we look at what's happening in the heart, this is requiring understanding of dynamic processes that occur over 9 orders of magnitude in space. The initiating events happen at the level, happen at the level of protein, ion channels and cells that regulate calcium going in and out to drive the heartbeat. These are arranged in some membrane that give a spatial and temporal heterogeneity of these type of systems. The cell then is a complex 3D structure that has all the molecular machinery that allows these things to happen dynamically. These cells are then embedded in a complex 3D tissue architecture, including heart cells, other type of cells, as well as passive materials. And of course, these then are wrapped up into an organ system with boundary conditions and all sorts of other complexities until you finally get to the body, which then these systems are intrinsically linked together. So this becomes a very, very complex system to even start to describe the physics of, much less try to do computational analysis of. So should we even try? I mean, is this a hopeless task? Is this something that's worth doing? Is this something that's sort of maybe a novel research project? And we think no, we think that there's a lot of motivation, especially when you think about biology and healthcare. the drive to include greater technologies, greater engineering solutions, gives us opportunities where our computer models might be incredibly useful. We've been looking at some of the biggest problems in cardiology, one of which is sudden cardiac death. And don't worry, this is just an actor. He's okay. But this is when the heart has a dangerous electrical rhythm, where the normal electrical rhythm of the heart gets disturbed. And instead of having synchronized pumping action, the heart flutters and is unable to perfuse the body. And this is a very common occurrence. If we look at US statistics, 500,000 people have this every year, with 95% dying before they reach emergency assistance. And I'm sure if we look in this building, we'll see one of these heart starters around. There might be multiple of them. These are ubiquitous because this can be cured, this can be fixed, and if we know you're at risk, you can actually implant a little defibrillator that can save your life. We also look at heart failure, and this is when, here's a nice little image of the heart, when some sort of injury or insult causes the left ventricle, the main pumping chamber, to dilate and thin, weaken, and it's a progressive cycle of dilation and thinning and weakening until the heart can no longer perfuse the body. And this is a huge problem in modern healthcare. Tens of billions of dollars spent every year in the US, and it's still effectively a death sentence with mortality at 20% at 1 year and 80% at 8 years. So these are problems where even small incremental changes to the practice of care could make a big difference in people's lives, make a big economic difference, and anything transformative could be huge for society at large. So with that backdrop of motivation of what we want to do, I'll just guide you through just briefly how we actually think about doing it. And at the cornerstone is still cardiac biology. We can't really kind of ignore biology. And in fact, we use hundreds of years of research, of detailed analysis to understand the processes that are occurring so we can model them effectively. We also have a strong background in computer science, mathematics, computer methods, advanced cluster computing. How do we actually solve the type of systems that we want to set up? So by combining these two expertise of cardiac biology and computer science and engineering, we can create specific methods and tools to study the heart, to actually do the type of analysis that we want to, and then hopefully transform these into meaningful domain-based research. Can we actually test and answer cardiac-specific hypotheses? And can we create applications that are useful, that can change the way doctors do work or give doctors more information about the types of problems that they're looking at? So just a couple things that we can kind of do, just briefly. I won't kind of go into all the topics that we're currently working on, but we can build models really to look at the pump functionality of the heart. Can we understand how motion abnormalities in the heart can correlate with interesting clinical features? Can we give new refinements to clinicians on trying to determine which patients need to be prioritized for treatment? We can also understand basic mechanical function. The heart is a mechanical system, and it undergoes, it has immense sort of stress and strain dynamics. And these stress and strain dynamics are incredibly hard, if not impossible, to measure, but they can be estimated from computational techniques. And these type of parameters are of use of both short, medium, and long-term prognosis in how the heart behaves. We can also use this to understand electrophysiology of the heart, the electrical activity of the heart, how signal propagates through the heart to create a synchronized beat. Here we have a little movie of the atria, the uppermost pumping chambers of the heart. And these normally beat in synchrony, but when there's a certain type of disturbance, this activation pattern breaks up into this spiral wave that causes asynchronous contraction of the heart. So instead of beating, they kind of flutter. This is a process called atrial fibrillation, and it's a big problem, and using models we can understand how it occurs and also come up with ways of trying to correct it. We can also look at other aspects of cardiac health, such as cardiac ischemia. A cardiac ischemia is when you have some sort of blockage and you try to, and some of the heart doesn't have enough oxygen and nutrients to beat. And there are methods of looking at this. You can give people radioactive dyes and put them on a treadmill. You can go in invasively, but we're trying to find non-invasive ways of doing this. So we can take, for example, the electrical signal on the body. These are called body surface potential measurements. And the standard one would be a standard ECG, which you get whenever you go in for a heart exam. And from this electrical activity at the heart, by using a model, we can go ahead and infer what is happening at the level of the heart. We can compare these to measurements made invasively or with radiation and try and come up with new, non-invasive, quick methods that can give insight into doctors on how the heart is behaving. And I like to be a little enthusiastic. Maybe I'm not quite enough of a pessimist, but we really think that we can use these two solutions to drive new innovations. And we're very fortunate. We have a RCN-funded research-based innovation project called the Center for Cardiological Innovation that we're a part of. And the goal of this is to produce commercially and clinically driven advances in cardiac diagnostics and applications. And this is a good way of integrating our type of work, of this mathematical modeling, with the clinic and also with industry to create advanced tools and novel treatments. We have a number of partners, and the type of work this allows us to do is really create patient-specific models. Can we take ultrasound, for example, and create a patient-specific model very quickly, very accurately, and then use such a model to study processes such as pacing? For example, electrical pacing, how the heart behaves is a common clinical approach. Can we understand how different pacing can cause different activation profiles and optimize this response at the level of the individual patient? And we really see ourselves as an integral part of an innovation process that requires tons of competencies, advanced sort of device providers, expert clinical guidance, and us as somewhat as the background of the mathematical modeling. And this is even more so towards the future, where we think this is all moving in towards a digital patient. Despite my quote from 200 years ago, mathematical modeling in biology is increasing in importance. The regulatory bodies especially are taking note of it, requiring it, coming up with guidelines for its use. And this will just continue as we improve our methods, improve imaging and diagnostics that help feed into our pipeline, the continued digitization of patient data, and especially increased computer power. And I think I have just time to talk about computer power for 1 second. We had a project working on the Tiana 2, which is was the world's most powerful computer. It changes every 6 months or so. And we were able to simulate 5% of one heartbeat on 2% of one cell using 20,000 core hours, or about 2.5 years on a single processor machine. And considering there are billions of cells in the heart, and we like to simulate over multiple beats, coming up with these very detailed physical representations is still years and years, if not decades out. But it's coming, and this is the type of thing that I think we'll all sort of live to see. So with that, I'll finish. I just want to acknowledge especially the Research Council, which has funded a lot of our work and has been very useful to us, the Norwegian Meta Center for Computational Science, as well as my group at Simula, and everyone here has contributed to these projects, as well as the members of the Center for Cardiological Innovation, especially Eigil Somset from GE, and Christina Hauge and Tor Edvardsen from Oslo University Hospital. So thanks, and I'm more than happy to take any questions.
Panel?
Yeah, thank you. Excellent presentation, and it's really an exciting field. For someone not, neither mathematics or IT, how sure are you that your simulations are right? I'm assuming you're not using crash test dummies or test subjects on this. So how sure are you that your simulations are getting it right?
Yeah, and I think that's one of the biggest challenges is validation and verification. Oftentimes, these models can get so complex that if not done right, they're just an exercise in a black box. You put something in and something comes out. It looks the same, so you say I've made a right model. So understanding what techniques we can use to validate and verify is a big part of this. And for example, we find proxies for the things that you can't measure, which would be indicative of our results. And if those can align, then you have some faith that your model's correct. It's all kind of incremental steps. Because eventually, when you can actually measure the types of things that you can use for the models, you won't need the models anymore. So we're always just trying to stay a little bit ahead and give things new, and at the same time verifying and validating.
You had a very brief slide on industrial cooperation. Are you at a point where your industrial partners can actually utilize your models at this point?
So,
And if not, when do you expect to be there? And what do you think the first problems they will work on will be?
okay, yeah, I think that's a really good question. Right now, most of the direct interest in our models is in providing support for simpler models. How can you make models simpler such that they can be done in real time in the clinic? And we can provide a lot of support for that. We have some projects ongoing that now we're kind of in the hours to kind of do the calculations. So those become tractable when you're dealing with clinical problems that might take weeks or months to plan over. If you have a heart failure patient, they're coming in for months and months and months, and then they're going to do a procedure in, say, 3 weeks, spending a couple hours to do some optimization, doing some simulation is not a big deal. If someone's coming into the ER with a blockage and you're going to try to use models and understanding where that blockage is, that's decades away. But I think that even now we're starting to see the clinical utility of models. Other groups are also using them with turnaround times of a day. So if the procedure is such that there's a time window for it, then this is where the models are going to come into play. But they're happening now. There are a number of venture groups, there are startups as well as some big industry have taken on some of these projects and are trying to move them forward.
It's a very interesting comment you had regarding the limitation in computer science to really follow biology. I think that was an interesting one. But the question I had was, I mean, you talk about mechanics, electronics, pipes and tubes and flows and such on. And we kind of have a situation in Norway now where we talk about transfer of knowledge between sectors, back and forth between, for example, oil and gas and other sectors. Mm-hmm. How much of this knowledge is relevant, you would say, beyond the beating heart as such?
Yeah, I think that there's actually, I mean, we have groups working at Simula on earth and oil and gas projects. And I think a lot of the background computational methods, a lot of the mathematical systems that we bring together and the techniques for solving them are generally applicable. And then this is really a kind of a focus on using those techniques into the heart. But we also have projects in the brain. We also have projects in flow and lungs. We also have all sorts of other projects that we like to apply the mathematical tools that have been developed generally.